A qubit is often described as a bit that can be 0 and 1 at the same time. That sounds magical, but it is also easy to misunderstand. The real idea is stranger, cleaner, and much more useful than a magic switch. A normal computer bit is simple. It stores one of two possible answers, 0 or 1, off or on. Every photo, message, app, and video on your screen is built from huge patterns of these tiny yes or no choices. A qubit is also a two-outcome system when you read it. If you measure it, you get 0 or 1. The difference is what happens before that moment. Before measurement, the qubit has a quantum state that can behave like a blend of possibilities. The easiest mistake is to imagine a qubit as a coin under a cup. Maybe it is secretly heads. Maybe it is secretly tails. We just do not know yet. A qubit is not quite like that. Its state can produce effects that ordinary hidden uncertainty cannot. A better starting picture is a spinning coin. While it spins, calling it only heads or only tails misses something important. But the analogy has limits. A real qubit is not a tiny coin. It follows quantum rules that let possibilities combine and cancel. The state of a qubit is not the answer you will definitely get. It is more like a recipe for the chances of different answers, plus a hidden direction that affects how the qubit will interact with other operations. That direction is what makes quantum computing interesting. Many teachers picture a qubit as a point on a globe. The North Pole represents 0, the South Pole represents 1. Other points represent different quantum states. You do not need the geometry today. Just remember that a qubit has more ways to be prepared than a bit. Measuring a qubit is like asking it a very specific question. In the standard question, the only answers are 0 or 1. After the answer appears, the original delicate state is no longer available in the same way. Measurement changes what you were trying to inspect. If you prepare one qubit in the same state many times and measure it many times, you may see a pattern. Maybe 0 appears about half the time, and 1 appears about half the time. One measurement gives one sample. Many measurements reveal the behavior of the state. At this point, it may sound like qubits are just fancy random number makers. They are not. The important part is that quantum states can interfere. Some paths through a calculation can reinforce each other. Other paths can cancel each other. Algorithms try to arrange that interference carefully. Think about ripples in water. When two peaks meet, the wave gets bigger. When a peak meets a trough, the water can flatten out. Quantum computing uses a similar idea with probability patterns, not water. The goal is to make wrong answers fade and useful answers stand out. If this kind of explanation helps, consider subscribing while we build the idea step by step. Quantum computing can feel intimidating when it starts with equations. Here, we are staying with intuition first, so the strange parts become easier to reason about. Classical computers use logic gates that flip and compare bits. Quantum computers use quantum gates that change qubit states. You can picture a gate as a controlled push on the point on that globe. It changes the state without measuring it, if the hardware behaves well. Some quantum gates have familiar cousins. One operation can turn 0 into 1 and 1 into 0, like flipping a bit. But other gates are more quantum. They move a qubit from a definite state into a balanced state where measurement could later produce either result. Superposition does not mean a qubit gives you every answer for free. It means the state can be built from the possibilities 0 and 1. The power comes only when operations guide those possibilities, so that measurement is more likely to reveal something useful. With two ordinary bits, you can store one pair at a time, like 0, 0 or 1, 0. With two qubits, the joint state can involve all four pair possibilities in a quantum way. But again, measurement still gives one ordinary pair at the end. When qubits interact, they can become entangled. Entanglement means the best description belongs to the pair, not to each qubit separately. Measuring one gives information connected to the other. This is not a secret message faster than light. It is a special kind of shared quantum state. Imagine two gloves packed into two boxes. If you open one and find a left glove, you know the other is right. Entanglement is deeper than that simple story, because the outcomes are not just pre-written labels. Still, it is important to avoid the myth that entanglement sends usable messages instantly. A single qubit is delicate. Many qubits are much harder. The computer must keep their states controlled, make them interact in precise ways, and measure them only when needed. The more qubits you involve, the more chances there are for small, unwanted effects to creep in. Noise means unwanted influence from the outside world or from imperfect control. Heat, stray fields, vibration, timing errors, and imperfect electronics can all disturb a quantum state. In a normal computer, a small disturbance often gets ignored. In a quantum computer, a tiny disturbance can matter. Decoherence is what happens when a delicate quantum state loses its special quantum behavior by leaking information into the environment. It is like trying to keep a whisper private in a noisy room. Once the room has picked up clues, the original fragile pattern is partly lost. A qubit is not one specific object. It can be built from different physical systems that follow quantum rules. Some use tiny superconducting circuits. Some use trapped ions. Some use photons, atoms, or defects inside materials. The shared idea is a controllable two-level quantum system. Different qubit technologies have different strengths. One may be easier to connect into chips. Another may keep its state longer. Another may be easier to move across a network. The field is not just about counting qubits. It is about quality, control, and useful operations. Measurement itself is also a hardware challenge. The machine must turn a fragile quantum state into a clear classical result. That result must be reliable enough to trust. A readout error is like asking a careful question and then having the answer written down incorrectly. In classical computing, copying information is easy. You can duplicate a file again and again. Unknown quantum states cannot be copied perfectly. This rule protects some quantum effects, but it also makes error correction harder. You cannot simply back up a qubit the normal way. Quantum error correction uses groups of physical qubits to protect one more reliable logical qubit. The trick is to detect signs of errors without directly measuring and destroying the information you want to keep. It is one of the central engineering challenges in building large quantum computers. A physical qubit is the actual fragile device in the lab. A logical qubit is the protected information made from many physical qubits working together. When people discuss future useful quantum computers, this distinction matters. More physical qubits do not automatically mean more useful computing power. Quantum computers are not meant to replace your laptop for everyday tasks. They are designed for special problems where quantum structure matters. Examples include simulating molecules, exploring materials, and speeding up certain mathematical procedures. For most ordinary work, classical computers are still the right tool. Nature itself is quantum at small scales. Electrons in atoms and molecules do not behave like tiny billiard balls. So using a quantum device to model quantum systems can be more natural than forcing a classical computer to track every detail in the usual way. Another common misunderstanding is that a quantum computer simply tries every answer in parallel and reads the best one. If it were that easy, every hard problem would collapse. The hard part is designing a process where interference makes the final measurement favor the information you wanted. No matter how rich the quantum state was before, the final measurement gives ordinary classical data. You see a string of zeros and ones. The art of a quantum algorithm is to shape the state before measurement so that this ordinary output is meaningful. A quantum algorithm is a careful recipe. prepare qubits, apply gates, create interference and sometimes entanglement, measure at the end. The recipe only helps if the problem has a structure that the quantum process can exploit. Randomly adding qubits is not enough. Many quantum machines need extreme isolation from the everyday world. Some systems are cooled to very low temperatures. Others are held in vacuum chambers or controlled with lasers. This is not for drama. It is because the environment constantly tries to turn quantum behavior into ordinary noise. Here is the mental model to keep. A bit is a definite answer. A qubit is a controllable quantum state that can be prepared, transformed, connected with other qubits, and finally measured. The state is powerful because its possibilities can interfere before the final answer appears. If someone says a qubit is both 0 and 1, treat that as a shortcut, not the full explanation. The better version is this. A qubit carries a quantum state. Measurement turns that state into a classical result. Noise damages the state. Good algorithms use interference to extract value. Qubits are not magic, and they are not just faster bits. They are a different way to handle information, built on the rules of quantum physics. If you still have a question, leave it in the comments, and tell us what future tech topic you want explained next.